bit about us. I mean, you probably already know who CCP Games are. My name is Terry Wilkinson. I'm the principal blockchain engineer at CCP Games. We're currently working on a Web3 integrated product, a game named Project Awakening. If you want to contact me after the chat in person is fine, or if you have any burning questions after that, feel free to shoot me a message on Telegram or email. So today I'm going to talk about a framework that we're building at CCP. And the intention for the framework is that it acts as the primary vehicle or the primary integration layer for third-party developers to interact with in-game mechanics and in-game objects. And so this is just an overview of some of the things that I'll talk about, some design considerations, maybe some design hurdles, touch a little bit on entity components and systems. Maybe lots of people know about that, a raise of hands. Have you heard of the ECS model? Yeah, good, okay. We'll talk a little bit about ECS in practice, what it looks like in standard Solidity design patterns or development patterns. What does it look like in MUD? And what kind of walls maybe we can run into in these cases. And then we'll talk a little bit about heterogeneous entity sets. So generally speaking, entities in the entity model are homogeneous. So you only have a universal set of entities and you treat them the same with whatever code you run on them. Maybe we want to do subsets or mutually exclusive sets of entities. How can we accomplish that? And then a little bit about the smart object framework itself, which kind of helps us solve some of these things that we're trying to accomplish. And a conclusion. So design considerations. So we want to build a framework, an SDK or an API on the smart contract layer for third-party developers to interface with our gaming product. But we are building a AAA gaming product. And so we need to establish a very clear set of rules for what we want to support in-game and what kind of functionality and behavior we want that to have, at least initially in-game. There's a bunch of, I don't want to say restrictions, but I'll say rule sets about the real world that maybe don't apply to Web3. So when you're building a gaming product, you have to worry about things like real regulation when you're building a product and releasing it to the community. You have to worry about things like maintainability of your product, security of your product, making sure that it's a good experience for your users. And so this might impose specific rule sets on what we want for the entities or objects that interact directly with the game. Security is also a part of this. We don't want bugs or unexpected behavior in the things that interact directly with the game. And so this kind of leads us into the second part, which is in addition to this, we also want to maximize kind of code reusage or modularity or code generalization, because otherwise it won't be useful for developers to come build things on. Yeah, we want to maximize composability. We want to maximize extensibility for third-party developers. And these are kind of at odds with each other. How do I implement or enforce a rule set for direct game-related activity without restricting the game space for others, for third-party developers? Specifically using the same code. So if I deploy a different set of code, obviously I can implement different rules. But what if I want to maximize code reusage? So we have a bit of a dilemma here between safety for a gaming product and freedom for the third-party developers, the developer community. So I'll talk just quickly on entities, components, and systems, because they're important for later. It seems like a lot of people are familiar. There's lots of definitions out there. I got this one off of GitHub. It seemed relevant for what I'm talking about today. So, entity componenting system describes an approach which promotes code reusability by separating data and behavior. And it has these characteristics. Entities, which are unique, uniquely identifiable. Components, which are just data types that don't have behavior by themselves. Entities can have more than one or more, 0 or more components. You can change components dynamically. And it has systems that essentially are entry points to control the behavior and state changes for these components. So if we look at ECS in practice, I call this a standard pattern. This is just like the normal development pattern. In Solidity, I'm using the Open Zeppelin ERC20 standard as an example. So if we were to identify entities and components here, I would say that the primary entities are accounts. They're the things that we're acting upon. And components are these two maps. A map of balances for those accounts and a map of allowances for those accounts. So this is where we store our data. These are the entities that we work on. As far as systems go, it's not really the ERC20 interface itself, but it's probably the implementation behind this that acts as a system. But essentially, it defines the rules and logic of what kind of behavior or functionality those entities are going to exhibit and how that affects state changes to the components. In MUD, it's very similar. So accounts would still be accounts. Components change from simple mappings to stores, which are comprised of tables. Entity IDs are your keys, and they all have records. In our case, this would be balance records and accounting records, and often those records have fields. Systems also are very similar. The standard implementation has this interface that you back by the logic in an ERC20 contract. On MUD, we also have a ERC20 interface, but it's backed by an actual well-defined system, modular system. So this is just a snapshot of like a homogeneous entity case. So here I have a T set of accounts. We can imagine this as a universal set of accounts. It's like all of the accounts that can be. And I interact with it by calling a transfer to another account. And then at the end of the day, it changes my state, either minusing from one and adding to the other, or whatever defined behavior that we have. MUD is very similar in this regard. Maybe there should be a little star behind the basic interface. There's a lot of differences that can occur, different ways to structure behind. So in the standard model, probably you're inheriting a lot of things. In MUD, you don't have to do this. You can keep things decoupled. But the interface, or the way it interacts, is basically the same. And I think that's because it implicitly counts accounts as entities. It doesn't explicitly define entities. Accounts are just implicitly entities in these systems. So what are the outcomes of these kinds of patterns? So entities are implicit. In MUD, components and systems are explicitly defined. You register them as resources into the MUD system. Entities are handled uniformly or homogeneously by default. So there's no chance to have different logic fire in this case, for any account. If you call a transfer function, it's going to fire the transfer logic regardless of which account you're using. So everything's handled uniformly or homogeneously. But we had a question, so like what if I wanted to build configurable or custom logic for a subset of entities? Yeah, what if I wanted to be able to have one set of entities that have kind of different configuration or different customized logic from other set of entities in the system without having to redeploy new different logic? Like what if I wanted to use the same base logic? So there's a couple of approaches that you could maybe use for this. The first approach, we kind of bake in the type of entity into the method call. So we add an extra parameter t. This would say what type of account we're talking about. People probably wouldn't want to do this because it would change the ERC20 standard interface standard. So maybe it's not the best approach, but it is approach. You could possibly have it as a wrapper around ERC20 logic, something like this. The second approach is you would explicitly set the type of your entity or your account. So you would say this account is a generic type, type number 1. Whereas some other account maybe could be a type where we implement tax logic. So when you transfer some tokens, instead of just a raw transfer, the entity or account gets taxed. But in this case, you have to have extra logic to set this. And the last approach is that you would just implement 2 different functions for each of the different kinds of functionality that you wanted. One would be like the plain transfer function, no taxes involved. The second one would be taxed transfer logic. So what are the consequences of these? It seems like achieving heterogeneity of your entity logic requires some sort of adjustment to the contracts themselves, and it usually involves some sort of hard-coded solution. So you have to change the code of the original implementation to be able to handle different kinds of logics for different entities. To handle new entity subsets, usually you also have to have new deployments of contracts. Yeah, some approaches maybe are better for this. You could use maybe delegation and proxy to deploy in point rather than just deploying a whole new set of base contracts. But still, regardless, usually it involves heavy deployment of the original base code. In all cases, the design decisions for entity handling, it still applies universally. So in the first case, it means that I still would have to define some type in my parameters. Everybody would have to do that who wanted to interact. So in the first case, whoever interacted with this contract has to define a T in their parameters, right? So that's a restriction that we've put on the developers who want to interact. In the second case, any developer that wants to interact with this has to call the set T. They have to define the T before they would call the transfer function. So we've kind of shrunk their development space. They're restricted to have to do it this way. And in the last one also, they would have to choose which function do they want to call for the different kinds of functionality. And the last thing is, the only way to avoid this seems, and I have a star here, seems, so in our research so far, there might be other ways, is that a redeployment of custom code is needed to handle subsets of entities in the exact way that you want, but still kind of not have reusability or need reusability for the original use case. So we devised a smart object framework. We've defined this in different ways before, but in this context, this is probably a relevant definition. So we call it a framework for handling heterogeneous entity behavior without interrupting or shrinking the development space of other independent actions or interactions by extending MUD with explicit definitions for entities. So MUD explicitly defines systems and tables, which are components currently, and also namespaces. But we also want to explicitly define entities and what kind of associative relationships those entities have with systems and with hooks and with other objects or classes. So we define two kind of entities here, classes and objects. They just have a very simple inheritance relationship. So objects inherit the system functionality and the hook execution of any class that they are a part of. Yeah. We don't have any nesting of classes currently. It's a little complex, and we don't need it to solve kind of the case that we need right now. Maybe in the future, we'll think about this. So we just keep track of all of these associations, and then we kind of hold them in storage so that we can use them later. So if we were going to go back and try to solve the heterogeneous entity case using the smart object framework, it would look something like this. So you'll notice that at the end of our transfer here, we now have a hookable modifier. So anything that you would want to exhibit this kind of behavior or functionality or design pattern on, you would put a hookable modifier. And so we still have the universal set of accounts. And if you didn't implement any hook logic here, it would behave like a normal transfer. But at the same time, for somebody else's set of entities, maybe they define a hook. And they say that that hook logic is our T1 logic, so type 1 logic. So it's the logic that is taxable. And then we associate that hook with a class, and we associate that hook with the transfer function. So these associations, we usually call it targeting. So we say your hook should target a system and its function, but your hook should also target a set of entities that it's going to execute for. And then in this case, we're going to associate one object, object B, with our class. And since objects inherit from their classes, it will inherit this hook functionality, and it will inherit the ability to call transfer for this object B. So then, when we call the smart contracts, we have A send to B, and it's hookable. Instead of doing a normal balance subtract from A and a balance add to B, we would invoke the tax logic inside. And this doesn't interfere with the normal set of entities. So as long as my entities are defined a certain way and other entities are defined a certain way, they can have two completely parallel behaviors at the same time. So this was kind of the solution that we came up for to solve our original problem, which is we at CCP need to have a very well-defined set of behaviors and functionalities and security assurances to build out a game product. But we don't want the way we build the code or the framework to restrict or stop other third-party developers from doing what they want. So we can do what we want with our entities. We can build a set of ships. Those set of ships interact directly with the game. But a third-party developer could come in and build a set of ships, and they could configure it or customize it completely differently, and they both can live in the same space happily. And in addition to this, they can both use the same system and module code at the same time without having to re-implement and redeploy. So yeah, we can achieve heterogeneous entity handling without any replacement of our original code base. Hook associations are not permanent, so you can remove a hook association and reapply it. So you could change your functionality on the fly if you wanted to for your set of entities. Two developers can independently use the same code base at the same time, but can define or customize their logic for their entity classes. No problem. We maximize the original code reusage in the ecosystem. We can maximize modularity, composability, and extensibility, but there are some trade-offs. And so what we found is the trade-offs are there's a lot of complexity in the configuration portion of this process, right? So yeah, I'm deploying less code. I have to write less systems, but I do have to write some hooks. I have to configure those hooks and target them in the right places. And it's a bit of a different coding pattern than before. And so that requires some extra learning curve. So maybe you guys have some questions for me, but I also have some questions for you. Like, as a developer, I would like you to think about, like, is this an acceptable trade-off? Like, do you want more freedom or more power to be able to extend or have more modularity or be able to compose and mix and match and build the things you want at the cost of complexity? Yeah. Thanks.